Mechanics note. Please write your next subheading, the law of conservation of energy. The law of conservation of energy. The law of conservation of energy. What's the meaning of this word here? Meaning of this word, conserved, mean there is no change. It's not changed. No change. That's the simplest meaning. Okay. The law of conservation of energy mean energy is not changed. What's the meaning of it here? Energy is not changed. Okay. So this law tells us total energy of an object or many objects is a constant amount. You cannot increase, you cannot decrease the total energy. The only thing that you can do is you can convert energy in one form to the other form. Kinetic energy into potential energy, potential energy into kinetic energy, kinetic energy into electrical energy into light energy again into electrical energy, and so on. We can convert one form of energy into another form of energy, but we cannot increase the total amount of energy, or we cannot decrease the total amount of energy of an object or a system. System means combination of many objects, more than one object. Okay dear? Right. So please write, the heading is the law of conservation of energy. Under that please write the total energy of an object or a system of objects. The total energy of an object or a system of objects, is conserved. The total energy of an object or a system of objects, is conserved. Okay? Read it for yourself, please. Read the law for yourself. Read. Star point and write. This law tells us. Tells us that the total amount of energy is a constant amount. Tells us that the total amount of energy is a constant amount. Okay, total energy is a constant amount. Same line, same point. The total amount of energy of an object or many objects. System means many objects. The total amount of object or many objects. Total amount of object of an object or many objects, is not changed. Okay dear? Next star point. The above law can be represented by the following equation. The above law can be represented by the following equation. The above law can be represented by the following equation. Look at board. If an object has a total amount of energy at the beginning, the initial total energy equals what? The final total energy. If an object has a certain amount of energy at the beginning, it must have the same amount of energy at the end. When I tell you like that, you can't understand anything. Therefore, we should discuss a numerical example. First, you write this. After that, we'll try for a numerical example. Then only you can understand it. First, you write it. Who wants more time to write this equation? Please write example. A coconut is dropped from a tree. A coconut is dropped. D-R-O, dropped. A coconut is dropped from a tree at a height of 20 meter. At a height of 20 meter. At a height of 20 meter. Full stop. Find the velocity of the coconut. Find the velocity of the coconut when it hits the ground. Find the velocity of the coconut when it hits the ground. Look at what here. Let's say this is there is a coconut tree. What tree here? A coconut tree. Try to grow better coconut tree than me, right? Drop means that's what will happen to you if you fail the exam. The people will drop you. Drop means release something at rest. Therefore, you will not feel that you have dropped by others. You didn't get it because you can't understand at this age, right? So a coconut is dropped mean what is the initial velocity? 0. That's what you can understand now. What's the initial velocity here? 0. That's the meaning of dropped. So it falls freely under the gravity and it hits the ground with the velocity of v meter per second. The question asks us to find the velocity of the coconut when it hits the ground. When it hits the ground. What is this height? The question has given us this height as how many meters here? 20 meters. Draw this figure. So please write, let us apply the law of conservation of energy. Let us apply the law of conservation of energy. Let us apply the law of conservation of energy. Then write down this equation. The law of conservation of energy. That initial total energy equals to the final total energy. Right? Write the equation and please wait. I'll help you. Let us apply the law of conservation of energy. Then write this equation. Please wait until I explain the rest. Coconut, it's a solid object. Am I right? Gas object, right? Coconut is liquid, no, solid. Listen to me. A solid object has normally something like a solid object, something like coconut has only two forms of energy. Two forms of energy. What are the two forms of energy here? Kinetic energy and potential energy. Kinetic energy and potential energy. When the coconut is falling downward, it emits light. Who has seen such coconuts here? Even no, hidden මිනිස්සු එලකෙන මම රහත් වෙලා කියන. Psycho. So coconut is a solid object. Solid objects such as coconuts, metal balls, rubber balls, gel balls, glass balls, they have only kinetic energy and potential energy. Right. So initial total energy means, let me consider initial point as A, you should also mark, and final point as B. Would you please mark A and B points on the figure? Initial total energy means, lamai, potential energy of the coconut at the beginning. Initially, the initial potential energy. Initial potential energy means potential energy of the coconut when it is at capital A. Plus kinetic energy of the coconut when it is at A. Summation of potential energy and kinetic energy is said to be the total energy of a solid object such as a coconut. Okay, dear? Similarly, total energy, final total energy means finally coconut is at B. Final coconut is at B. So potential energy of the coconut when it is at B plus kinetic energy of the coconut when it is at B is the total final energy or final total energy. Finally coconut is at B. Therefore, total final energy or final total energy means summation of potential energy at B and kinetic energy at B. Is it clear? Right. There is nothing to explain in it that much. Potential energy is mgh. Kinetic energy is half m u square, u for initial velocity. Again, potential energy is mgh, kinetic energy is half mv square, v for final energy, final velocity. When we write like this, we have a problem. Don't write, just look at the board and tell me what's the problem there. Kinetic energy, no problem, half mu square, half mv square. What about the potential energy? Here also mgh, here also mg H. So students may be cancelled, MGH to MGH may be cancelled out. To indicate MGH terms separately, this is normally marked as MGH1 and this is marked as H2. Okay dear? Do we know the mass of the coconut? Don't write anything. Do we know the mass of the coconut? Don't know. Read the question. Is it given in the question the mass of the coconut? No. Is the mass of the coconut given? No. If the mass of the coconut is not given, don't worry about the things that you don't know. Think only about the things that you know. So just forget about M. Keep M as MRG. 10. H1 is the initial height. Initially coconut is at a height of 20 meter. 20 meter. Plus half mass. What is the initial velocity? Dropped mean initial velocity is 0. Dropped mean initial velocity is 0. So initial velocity is 0. M Ulaigal G 10. H2 height is the distance to an object from the ground. Height is the distance to an object from the ground. Object is on the ground. Therefore, distance to the object from the ground is 0. This height means distance to any object from the ground. Now, object is already on the ground. Therefore, distance to the object from the ground is 0. Therefore, final height is 0. Who would like if I explain this again? Anybody in the class? Okay, good. Then half m, what is the final velocity? V square. Now what will happen to these m terms here? So simple, all the m terms are cancelled out. Or think that we have divided all the terms by m. If we divide all the terms by m will be cancelled out. Can you do the rest and find v? Friday? Find v. So who found the value of v? How many?
20.
Who says velocity is 20 meter per second? Oh, very good. Okay. So what are the remaining terms here? Is it difficult to separate the terms here? This is mgh1. This is half mu square. This is mgh2. This is half mv square. Okay. 10 into 20, 200. Plus half into 0, half of a 0. 0 into anything? 0. 0 into anything? 0. Equals 10 into 0, 10 zeros. 0 into anything? 0. 0 into anything? 0. This is half v square. So finally what are things you have? 200 equals half v square. Take 2 to this side. Then what will happen? Right there. Then what will happen? 200 multiplied by 2 equals v square. Therefore, v square is 200 times 2, 400. If v square is 400, what is v? Then v is square root of 400. What is square root of 400 then? 20. So v is 20 meter per second. Complete. And who got this answer? Online students, you can use the Zoom chat or raise your hand up in Zoom so I can identify that you have answered. Is everything okay? Any doubt? Right. Before the next example, let me show you something. So we try for the next example. Let's say there is a string. One end of the string is connected to a tall support, like this roof of the this roof. You connected to a tall support one end. The other end is to the other end a metal ball is connected. What is this here? A metal ball. Initially, the metal ball is kept at rest at a height of at a certain height from the ground. Once this is released, what will happen? When this is released, the metal ball will be moved along a curved path. Am I right here? Because of this is a string. Because of the string, the metal ball will be moved along a certain curved path. Okay, dear? I should draw the ground rule also. And when this is the lowest position, because after that it will again start to go up. It is coming down because height is reduced. So this is the lowest position. The lowest position of its path, because after that it will again move up. Okay, so now we are going to find the velocity of the metal ball when it reaches to the lowest path. Please write next example. Example: one end of a spring, one end of a spring is connected. One end of a string is connected to a tall support, and a metal ball is connected to the other end. One end of a string is connected to a tall support and a metal ball is connected to the other end. Full stop. Initially the ball is kept at capital A. Initially the ball is kept at capital A by keeping the string stretched, S-T-R-E-C-H-E-D, stretched. Initially, the ball is kept at rest at capital A by keeping the string stretched. The initial height of the ball is 2.4 meter. The initial height of the ball is 2.4 meter. Full stop. When the ball is released at rest at capital A, full stop and continue. When the ball is released at rest at capital A, when the ball is released at rest at capital A, comma, it moves along a curved path. As shown in the following figure. When the ball is released at rest at capital A, it moves along a curved path as shown in the following figure. First off, find the velocity of the ball when it reaches to its lowest position. Find the velocity of the ball when it reaches to its lowest position. Draw this figure.